but I could also put it in the chat. Do you see it in the chat?
Yeah.
Yeah.
Okay. All right, so here we go. So this first one, first I'm going to get all of the x values. And then put those on the graph. So here's my x and y axis. I need a -5. I need a -3, a -1, a +1, and a +3. Okay, so that part's done. And then this whole line right here is saying that the y value equals 0 for all of those x values. So then I'll just put a dot at -5, 0, -1, 0, 1, 0, and 3, 0. So that part's done. And then this part is saying on the left side of 0, the function is going up to infinity. So I'll just put a little indication like that for right now. But then this side is saying for the right side of 0, it's going to be a y value of 2. So it does something like this. It's going towards 2. And then as x approaches 1, both sides are going to be 0. So since I already had this part, I could like connect it, have it go to 0. And at this point, I don't know if it should bounce back up or if it should keep going. So I'll just put both of those possibilities for now, and then I'll take care of it later. Next up, the derivative is equal to 0. So at -3, the derivative equals 0. So I'm starting to think that it's probably going to look something like this, sort of like a parabola shape in here. And then it has to go through at -1, and then that side has to go up. And then down here, the derivative would equal 0. And the last part is at 1, the derivative does not exist. So now I'm thinking that having it bounce up right here at 1 is probably the way to go. Because if you make a corner or a cusp, the derivative doesn't exist. So now let me clean this part up. So I think it should go like this. And then make either a corner or a cusp. I'll try to make a cusp, except my pen is not cooperating. And then it also has to go through where x equals 3. So then it could go like this. It's not the prettiest graph, but I think that's it. Try to make it look a little bit better. So it goes down here, the derivative equals 0. It goes up, and then it's going to go up to infinity. The derivative equals 0 down there. And then right there, I tried to make a cusp. I guess I could just make a corner. That would make it look better. Because then I could go from 2 and then just make a straight line. And then make a straight line for a little while so that that is a corner. And then just have it go around and then go through 3. All right. That's number one. Any questions? Okay, on to a much more important topic, number two. So when you graph this, you know what kind of shape it makes?
Is it a circle?
It's a circle. Now, there's a couple of ways that you could look at a circle. One is, well, it would be a circle with a radius of 3. On account of that 9 is actually the radius squared. So the radius of the circle is 3, and it's centered at the origin. So there's a couple of ways you could look at a circle. One is it's just a round object. Another way to look at it is this could be like a tire that's going around and around and around and around in the same circle. So there's two ways to, at least two ways to look at a circle. Okay. First find dy dx. Now there's a couple of ways to do this. If you use the idea that you usually have a function that goes y equals whatever, x to the third, and then y prime equals 3x squared. So that's called explicit differentiation. Explicit differentiation. Because right here, I explicitly was able to solve for y. The way that this one is, I didn't solve for y, so this is an implicit function. So implicit so the word implicit is coming from the word imply. So it's implied that y is a function of x for this one. Because if you plug in something for x, like if you plug in that x equals a 0, then you'd be able to solve for y, and you'd get y equals plus or minus 3. So I'm going to do the derivative both ways, the explicit way and then the implicit way. So first of all, if I'm going to do it the explicit way, then I have to solve for y first. So then I would need to go y squared equals 9 minus x squared. And then the point that I'm talking about is approximately right here where x is a 1 and y is a 2 radical 2. The reason I'm saying that is because in the next step, in order to get rid of the square, I need to square root. And usually you're supposed to go plus or minus the square root. And the plus will give you the top half of the circle, and the minus will give you the bottom half of the circle. Because I'm talking about this point right here where y is positive, I don't actually need to put the plus and minus. I can just use the plus. Okay, so now find the derivative. And for derivative, you can say dy dx, or as a shortcut, you could say y prime. So I'll go y prime equals. So this is a square root function. So the derivative of a square root is 1 over 2 times that square root. And then the chain rule. So I took the derivative of the square root, but so far I haven't taken the derivative of the 9x squared. So now I need to do the chain rule and take the derivative of that and multiply. So the derivative of 9 minus x squared is going to be a negative 2x. So then I said find the derivative at that point. So that means that I need to plug in x equals 1. So y prime equals, so on the top there would be negative 2x, so that would be negative 2 times 1. And the bottom would have 2 times the square root, 9 minus 1 squared. And then these 2's could cancel. And it would be negative 1 over the square root of 8. And then square root of 8 could be simplified as 2 radical 2. Does anyone have questions on that one so far? Okay, now what we just found is if you take a tangent line and then it hits right at that 1 point right there, then the slope of that line is negative 1 over 2 radical 2. And it's going down, so having a negative slope is definitely correct. All right, so that's slope. Now I'm going to go back, and instead of doing the explicit differentiation, I'm going to do implicit differentiation. And we're going to get the same answer, and it's going to be less work. So for implicit differentiation, you just start taking the derivative. So you take the derivative of x squared, that would be 2x. Now, what I just did was the power rule, but technically the chain rule says you're also supposed to take the derivative of the inside. Well, the inside of this function, what's inside of that function is just an x. So take the derivative of x, and that's going to be a 1. So multiply by 1. Plus, now move on to the y squared. And its derivative would be 2y. And then I need to do the chain rule. So take the derivative of the y. And so you could call that dy dx, or you could call it y prime, whichever. And then on the right side, what's the derivative of 9?
Would it just be 0?
That is 0. Okay, so then I was supposed to find dy dx, so I need to do the algebra to solve for dy dx. I will leave 2y and dy dx on one side, and then just subtract the 2x from both sides. And then I could divide by 2y on both sides. So the derivative, and the 2's will cancel. So the derivative is negative x over y. Which looks a lot different than when we did the derivative before, but watch when you plug in the numbers. So now plug in the x and the y. So on top, replace the x with the 1, so it's going to leave negative 1. And on the bottom, replace the y with 2 radical 2. And then we got the same answer as last time. But did it with implicit differentiation. Anyone have questions on that one? No? Okay. Then on to the next part. So for the next part, notice that it's saying take the derivative, but with respect to t. So when I first started talking about the circle, I said there's two ways you could look at it. One is it's just a round object and that's it. Or it could be something that's going around in a circle, and then you're supposed to find out how fast it's going. Well, that's what this is talking about, because this is feet per second. So that is a velocity. So even though you don't see any t in the equation, well, for an object to go around a circle, the time has to pass. So there is time, just like right now, the time is passing, even if you're not watching a clock. So time is passing, and so the object is going around the circle at some kind of speed. All right. Then use the implicit differentiation. So start over. So taking the derivative of x squared, that's going to be 2x. So that was the derivative of the squared function. And then the chain rule says you still need to take the derivative of this x. Well, when I did it before, it was a 1 because I was taking the derivative with respect to x. So technically this one was take the derivative of x with respect to x. And then dx divided by a dx, that's equal to 1. But now that we're taking the derivative with respect to t, it's going to be take the derivative of x with respect to t. And then moving on to the y squared, it's going to be 2y, and then take the derivative of y with respect to t. And the derivative of 9 is still 0. So let's say this is the object, this red dot right here is the object, and it's going around the circle. So as it moves, let's say it moves from the first dot to the second dot. So it's going this direction. So in that case, the red dot, well, it had to move to the left and it had to move up. So it's basically going up and also to the left. Well, this part right here, that's saying how fast is it changing the x direction? So that is how fast it's going to the left. And then this is the y information, and that is how fast is it going up? So it's going both to the left and also up. Okay, so then, like last time, solve for the dy dt. So I could leave the 2y dy dt here, and then subtract 2x dx dt from both sides. And then to solve for dy dt, just divide both sides by 2y. So the 2x, the negative 2x, and dx dt would stay there, and then divide by 2y. And then these 2's could cancel. And just like last time, plug in the numbers. So dy dt will equal, so it was a negative, and then x was a 1. And then right here in red, it was given that dx dt is a negative 1 feet per second. So it's a negative 1, and this is going to be in feet per second. And then on the bottom, it's going to be the 2 radical 2 for the y value that was given at the beginning of the problem. So the dy dt would be what, a positive 1 over 2 radical 2. So positive 1. Oh no, my battery's dying. Divided by 2 radical 2 is a 0.354 feet per second. And this one right here is positive because it's going up as it goes from the first red dot to the second red dot. So that's how fast it's going up. And then this part means it was going to the left by 1 foot per second. Any questions on that, or shall we do part C? Okay, so once you get used to this, you could also do it like this. So again, start with the same equation, x squared plus y squared equals 9. And then for the derivative of x squared, that would be 2x times x prime. It's just faster and easier to write it that way rather than the dx dt, but they mean the same thing. And then plus 2y times y prime. Now, over here, I did the algebra first, and then I plugged in the number. Well, you could plug in the numbers first and then do the algebra, because that's going to make the algebra easier. So this would be 2, and then x is a 1, that was given. So we're solving for dx dt, or we're solving for x prime. So that just stays there. And then 2 times the y value was 2 radical 2. And then this was given that the y prime is equal to -1. So let's see, this would be 4 radical 2, but with a negative. This would be 4 radical 2 with a negative. So move it to the other side and it'll become positive 4 radical 2. And then on the left side, all that's left is 2 times x prime. And then last, just divide by 2. And x prime is going to equal 2 radical 2, which is 2.828 feet per second. But wait a second. Didn't I say it was going to the left? If things are going to the left, their derivative should be negative. But this one's positive. The reason for that is right here, I said dy dt is equal to a -1, which means it's now going down. So for part C, it's actually going this direction. It's actually going this direction because it's going down and then it's going to the right. So if it's going down and to the right, that means that this derivative, yep, was supposed to be positive. So that's the beginning of implicit differentiation. And now on to some straightforward, just practice derivatives. So if you have just secant of x, can somebody tell me what the derivative of secant of x is?
Secant of x times tangent of x.
That's true. So an important thing is, whatever this is x, it has to be the same right here and right here. So now I'm ready to do part A. So when I take the derivative of this secant, it doesn't just have an x right here. So this is getting replaced with secant of x. That means this also has to be the secant of x, and this also. So to begin with, the derivative of that first secant is going to be secant of whatever's in the parentheses times tangent whatever's in the parentheses. And that would be an extra secant of x. And now we're not quite done, because then the chain rule would say, hey, you never took the derivative of this secant that's inside the parentheses. So then do the chain rule. And the derivative of that secant would be secant of x times tangent of x. So could it be simplified? It sort of looks like you could somehow combine these secants or factor them or something like that, but you can't because this one is stuck inside of a secant function. And then this one is stuck inside of a tangent function. And so just like if you had tangent of x squared times x to the cube, you might want to say, oh, I'm going to put these x's together, but you can't because this one is stuck inside of a tangent function and then this one is outside of it. So it can't be simplified. All right, then on to part B. On part B, if it only said tangent inverse of x, you know what the derivative of that is? Anybody?
Would that be secant secant inverse squared x? Squared of x?
Oh, I don't think we've done the inverse functions yet, right?
No, we haven't.
Oh,
No, I don't think we've gone over those yet.
okay. Well, it's tangent inverse. The derivative of tangent inverse is this one right here. It's going to be 1 over 1 plus x squared, which seems weird because it's not even a 1 over 1 plus x squared. That's not even a trig function. But it turns out that is the derivative. So it's just a 1 over 1 plus x squared. Oh, let me go back to today's, there it is. So for tangent inverse, it's 1 over 1 plus x squared. And again, if this is, whatever this is for x, the exact same thing has to go right there in the formula. So when we go to do part B, when I take the derivative of tangent inverse, that's going to be 1 over 1 plus, and then whatever the argument is, or whatever's in the parentheses, that has to be squared. So the square root has to be squared. So that takes the care of taking the derivative of tangent inverse, but then the chain rule is going to say, by the way, you still need to take the derivative of square root of x, multiply with that. And the derivative of square root of x is going to be 1 over 2 times the square root of x. And then this one could be simplified a little bit. So right here, when you square the square root, that's just going to be 1 plus x. And then right here, we're multiplying on the bottom, we're multiplying by a 2 radical x. So you could either put that in the front of the parentheses or behind, but it would be like that. And for this one on the bottom, it's best to just leave it like this in factored form, because later you'll be asked, when does the derivative equal 0? So that is when the top equals 0. And also, when is it undefined? So that would be when the bottom equals 0. So for this one, y prime equal to 0, that means the top has to equal 0, but 1 never equals a 0. So this one would have no solutions. And when is y prime does not exist? Well, if x was a 0, that would cause the bottom to equal 0. Or if this equals 0, so that would be x equals -1. Also, x equals 0. That's where the derivative does not exist. Okay, then on to part C. So if the function was just e to the x, this is the easiest derivative there is. You know the derivative of e to the x?
E to the x.
Yep. It's the only function that the derivative is equal to itself. So to begin with, well, this one actually has 3 functions because it has the e, it has the square function, and then it also has the secant function. So we're going to have to take the derivative of all 3 of those, but only one at a time. So the outermost function is e. So the derivative of e to the secant squared will be e to the secant squared. Now the chain rule says take the derivative of this secant squared. Well, because it has a squared, use the power rule. So the 2 goes down in front and multiplies. Then subtract 1 from the exponent. So it's just going to be secant. So that's the derivative of the square function. And then take the derivative of secant. And then derivative of secant is secant of x, tangent of x. And then to finish this one, it could be simplified a little bit since this says secant times secant. So it's going to be e secant squared x, and then times a 2 and secant squared x, and times a tangent. And then part C is done. So for part D, the derivative of sine inverse. So the derivative of sine inverse, also, it's not a trig function for its derivative. It's 1 over the square root of 1 minus x squared. So for this one, the derivative will equal 1 over the square root of 1 minus whatever gets squared. So that's essentially the derivative of sine inverse. And then whatever's in the parentheses right here, that's what has to go right here. So that's going to be e, whoops, I need a pen. Now it's going to be e to the x inside the parentheses. And then the chain rule goes, all right, now it's time for the e to the x. Take the derivative of e to the x, which is e to the x. And then this one could be simplified. But how do I write it? Do I write it like this? Or do I write it like this? So when you raise a power to a power, like if you had x to the third raised to the seventh, how many x's is that? X to the what?
Would it be 10?
It's going to be 21. So when it's a power raised to a power, you multiply those two. If it was x to the third times a different x to the seventh, then that would be x to the 10. But when it's a power raised to a power, you multiply.
Okay.
So that means that these two should be multiplied, so it should be 2x. So this one was correct, although we don't really usually write it as x2. We usually write it as 2x. So this would be e to the 2x. And then that one cannot be simplified anymore, so it's done. Does anyone have questions? Okay. Then on to taking derivatives, but what if the letters were different? So instead of using x and y, we're going to use w and a as the variables. And this is another example of implicit differentiation. Okay, here we go. So first of all, this part right here is a product, so I have to use the product rule. So take the derivative of w squared. So that would be 2w. And then the chain rule would say, now you need to take the derivative of w itself. So that would be the derivative of w with respect to a. Then for the product rule, you just leave a alone for right now. And then plus, this time leave w squared alone. And now take the derivative of a with respect to a. So that's going to be a 1, because dA divided by dA is equal to 1. Plus, now do the product rule for these two right here. So there would be, first of all, the derivative of a squared would be 2a. And then take the derivative of a with respect to a. And just leave the w alone. And then just one more. This time, leave the a squared alone. And now take the derivative of w with respect to a. And on the right-hand side, the derivative of 2 is 0. So the directions said solve for dw dA, and there happens to be one of them right there, and there happens to be one of them right there. So what I'm going to do is group those two together. So let's see, this one would be 2wa dw dA. And then I'm going to move that one closer to it. So plus a squared dW dA. And then for those terms that don't have the dW dA, subtract them and put them over on the right side. Now this one, dA over dA is just a 1. So that means that this one really just equals W squared. So subtract W squared from both sides. And this one, the dAs can cancel, so it just leaves 2AW. So subtract 2AW from both sides. And then there's just 2 more steps. So this one has dWdA and this one has dWdA. Since they're the same, you could factor it out. dWdA gets factored out. And then what remains is 2WA plus A squared. And on the right side, there's still minus W squared minus 2AW. And then the last step is divide both sides by this 2, by this 2WA plus A squared. So dWdA equals negative W squared minus 2AW, and then divide both sides by 2WA plus A squared. And then that one is finished. Is everybody still awake? Thumbs up. 2 thumbs up. Jose might be taking a nap.
No, I'm still here.
Oh, okay. Okay, so now I need some space so I could do this part B. Okay, so for part B, still taking the derivative with respect to A. So on the left side, it's going to be take the derivative of A with respect to A. So that's going to equal a 1. On the right side, the derivative of sine is cosine. And for right now, the A and W stays there. And then do the chain rule. Now taking the derivative of A and W. So there would be the derivative of A with respect to A, and then leave the W alone, plus now leave the A alone and take the derivative of W with respect to A. Just barely made it on the edge of the screen. So then we need to solve for the dWdA. Well, for one thing, I could get rid of this cosine if I divide both sides by the cosine. So on the left side, dA divided by dA is a 1. So it's basically saying 1 divided by cosine. So which trig function is 1 divided by cosine?
Secant.
That's secant. So it's going to be secant of AW. And now this is gone. And no, don't do that. Thank you. And then what's left is dA divided by dA is a 1, so it's going to be 1 times W, or just W. And then plus the A times dW dA. And then there's only 2 more steps. One is subtract W from both sides. So that'll be secant of AW and then minus a W equals A dW dA. And finally, the very last step to solve for dW dA. So that's secant of AW minus W, and then divide both sides by A, and then it's done. Next up, how about the function sine the square root of x? So on the problem set, I have one that was similar, but it was sine of x squared. But let's look at sine square root of x. Clear that out. So y is equal to sine the square root of x. And then change the window to go from 0 to 2 pi. And sine ranges between -1 and 1. And then what does the graph look like? So it looks to me like there's only going to be one place where the derivative equals 0. Right up here at the top of it. That would be a horizontal tangent line. So where's that? That's at about, x is about 2.2 or 2.3 or so, 2.26. Let's see. So graph the function, it just looked like this. So there was actually just one maximum. Now, technically, when you're given an interval and asked about minimums and maximums, then you should also check the endpoints. So if I go back, so over here, the function is going through 0, 0. And so actually that's the lowest point on the graph. So that's not going to be about the derivative. That's just if you plug in 0, then sine of 0 is 0. So this is actually the, on that interval from 0 to 2 pi, that's the lowest point, 0, 0. And then we'll find out what this point was. So find the derivative. So the derivative of sine is cosine. So that'll be cosine the square root of x. And then the chain rule says, now it's time to take derivative of the square root of x. So that's going to be 1 over 2 times the square root of x. Or you could rewrite this as the numerator has cosine the square root of x times 1. So that's just the square root of cosine x. And the bottom has 2 radical x. And then I said, where does the derivative equal 0? Well, in order for a fraction to equal 0, the top has to equal 0. If I also said, where's the derivative undefined, then we would also do the bottom equals 0. If we did the bottom equals 0, that would actually give us this point. The derivative is not defined there because it's not continuous. But for this one, where's the derivative equals 0? That means the top equals 0. So cosine of the square root of x equals 0. And if you look at the cosine function, where it equals 0, well, over here would be 2 pi, and in the middle would be pi, which means this one is pi over 2. This one would be 3 pi over 2. But when I looked at the graph, I only found one maximum, so I only need one answer. So I'm thinking it's going to be the pi over 2. But this part doesn't say x equals pi over 2. It says square root of x equals. So square root of x equals pi over 2. And then to solve for x, just square both sides. So pi over 2 gets squared. And when I looked at the graph, I think it was like 2.26. Let's see. Was it 2. There's the top. No, 2.46. So is that pi divided by 2 gets squared? Yep, sure enough, that's it. The math will never lie to you. So 2.467. So 2.467. And then where's the function increasing? Or in other words, where's the derivative positive? Well, this point right here, for the maximum, this point right here was x is a 2.467. Was that right? 2.467? Yeah. So that means this is the part that's increasing. And this part would be decreasing. So it's increasing from 0 . So it's increasing from 0 until it gets to the 2.467. So it's increasing from 0 to 2.467. And then do I use round parentheses or square brackets?
Round parentheses.
That is true. Because if I put the square brackets, that would mean that at 0, it is increasing, which means that the derivative would have to equal, would actually have to be a positive number right there. But the derivative doesn't even exist because it's not continuous on the left side. And then also at 2.467, that's when it's at the top, and the derivative would equal 0, which is not a positive number. So it's only between those where the derivative is positive. So it's supposed to be the round parentheses. And then I didn't know if we were going to have time for this one, but I just thought that would be fun. What about the second derivative? So right here is where I have the first derivative. And then what about the second derivative? Well, we only have 4 minutes, so I'm gonna have to go fast. So for this one, use the quotient rule. And the quotient rule says start on the top, take the derivative of cosine. So derivative of cosine is negative sine of the square root of x. And then the chain rule would say you still need to take the derivative of square root of x. So that's going to be times 1 over 2 times the square root of x. So that's the very first part of the quotient rule. The other part of the quotient rule says, now multiply that by the b, or the denominator. So multiply that by 2 square root of x. So that's half of the quotient rule, or actually it's like 1/3 of the quotient rule, because next it goes minus. Now leave the top one alone. And then take the derivative of the bottom one. So the 2 would just stay there. And the derivative of the square root is 1/2 times the square root of x. And finally, for the last part of the quotient rule, just take the bottom part, put it in parentheses, and square it. And then to clean up this answer, this 2 radical x and this 2 radical x will cancel each other out. And these 2's will cancel each other out. And then this thing right here is causing a complex fraction, so I need to get rid of that. So then multiply the top by a radical x and multiply the bottom by a radical x. And then we'll be done. So when you distribute the radical x over here, personally, I would just put that in front of the sine x. So, I mean, the sine squared x. So the radical x and the negative sign could go in front of sine radical x. Then the rest of this stuff canceled. When you distribute it over here, they're actually going to cancel each other out. So all it leaves is minus cosine radical x. And then this part needs to be squared, so that would be 4x. And then this purple radical x, you could just leave it like that. And then it doesn't need to be simplified anymore. Wow, what timing, 12 o'clock exactly. Just made it. Well, does anyone have any questions?